All right, in this video, I want to talk about the concept of surface integrals. And before I do, just want to put a little disclaimer out there. I'm assuming that you've had a previous discussion in another class, or maybe you saw in another video, the idea of surfaces given parametrically by vector valued functions. You'll notice, again, that's what I have right here. We're used to curves being given parametrically as, vector value functions R of t. And so this is a similar thing, but because we're talking about three-dimensional surfaces here, we need two independent variables, u and v. Okay, but as I said, I'm making an assumption here that you're familiar with surfaces given parametrically from your previous experiences. Okay, what I want to do this time is I want to find a way to calculate the area of such a surface. Okay, so for example, suppose our surface looks something like this. Okay, given parametrically by r of u and v. Right, so we imagine then that there's a vector anchored at the origin, if you will. That's actually drawing out the surface, right? As the parameter values u and v change, we imagine that this arrow is moving along and it's actually painting in the surface. What we want to do is we want to find its surface area. It's pretty clever, but it's kind of an old story. So what we'll do, think of it like this, guy. Think of breaking up the surface into little patches, something like that, right? And we'll call the area of that tiny patch D capital S. We don't want to use lowercase s. That's kind of reserved for arc length, right? So we'll call this a differential element of surface area. So now that's kind of tiny. So what I'm going to do is I'm going to magnify that a lot down here. So maybe we got this little patch of the surface, or maybe even that much of it, like that. I'll magnify that much of it and I'll include the patch in there, but something like this. Okay. And I'll put the X, Y, Z coordinate system on there, or axes, just for perspective. All right. And we'll say that this is our patch. And let's do this. Let's call this corner right here. We'll say that corner is given by R of U and V. Okay, move my calculator here. There we go. And then let's call this one over here. We'll call that R of U plus delta U, V. And then this corner up here, let's call that one R of U and V plus delta V. Okay. I don't need this corner over here, so I'm just going to do those three. Okay. Let me make these vectors just a little heavier in type. Like that, just so you can see them a little bit better. Okay. Again, the next thing I'm going to do is this. Let me use a different color. Let's make the vector from this point to this point. Okay. Now, of course, that green vector in there, right? That's actually this, huh? Okay. And then let's make this other vector, let's make this one blue, from one point here to this point. Okay, so that blue vector, you know what that is? That is this. Okay, how's that look? Why does that matter? Because again, in your earlier work, remember, notice that the blue vector and the green vector, they're actually adjacent sides of a parallelogram, right? And I can draw my parallelogram like this. I'll use red for that, okay? And notice that the area of that parallelogram is essentially the same as the area of the little patch underneath of it. In other words, the differential element of surface area, ds, is approximately equal to the area of that parallelogram. Now, what is the area of that parallelogram? All right, well, from our earlier work, we know that if we first take the cross product of these two vectors and then find its magnitude, that will give us the area of the parallelogram. Okay, so we'll just do that right here. Let's see. All right, so I'm going to take that one vector, and then I'm going to cross it with the other. That. Then, of course, we have to take the magnitude like this. Okay, how's that look? And then I'm going to be clever, gang. I'm going to multiply by a clever expression of 1, like this. Isn't that clever? That's my clever expression of 1. Okay. Now, hopefully, those expressions, those fractions, are looking pretty familiar to you. You should recognize those as difference quotients. Okay. So naturally, the next thing we're going to do is we're going to take delta x to go to 0 and delta y also to go to 0. So what happens is the parallelogram shrinks, so does the patch. And that approximation becomes better and better. We say actually exact in the limit. And so we say then that the differential element of surface area is actually equal to the magnitude of these things. In the limit, they're actually the very definitions of the partial derivatives of r with respect to u and with respect to v. Okay. And mind you, again, now that's just one patch on the surface, right? We imagine that the surface is made up of an infinite amount of those patches. And so we say then that the total surface area, capital S, is the sum of all those differential elements as they range over the entire surface. Be careful now, there's two differentials. It's going to require two integral symbols. We write like this. Okay. And this is equal to, now remember from your earlier work, okay, again, another assumption is that you studied multiple integration. What do we usually represent the product of differentials by? du and dv or dx and dy? Right, dA for short, okay? And also from our experiences, if we have a dA here, what's the letter that goes down here? Right, the letter R, the region R, okay? Now, remember everyone, the region R in this case would be, because dA represents du dv, the region R is in the UV plane, okay? It's very clever. We call this, again, we call this a surface integral that represents surface area. And I'm just going to make one quick little note here at the bottom. I ran out of, ran out of paper here, but I'm just going to mention this. And I'm going to say, see, move this up. Let's say in general, okay, in general, a surface integral has the form like that. Okay, we said in general, a surface integral has this form. If the integrand itself represents a constant, in this case, let's say the constant 1, then it actually defaults to the integral right here and represents surface area. If it's any other constant, you can set that constant aside, and it becomes a constant multiple of surface area. Okay? But this is, again, we call this a general surface integral. To solve it, well, let me ask you this. How did you solve line integrals of this form? You remember how to do that? Right. You have to put them in parametric form. That's right. You put them in parametric form, right? We write like this. Okay. The parametric equations for X, Y, and Z. Okay. The differential element of arc length. Okay. And the curve C, of course, is given by the vector value function R of T like this. Okay. That's how you evaluated line integrals, scalar line integrals. You put them in parametric form. Well, a general surface integral is no different. Okay. Just our surface this time is given parametrically, right? Remember, our surface S is given parametrically by these components. Okay. So our general surface integral here is going to look like this. Okay. The differential element of surface area. Okay. Look how close these integrals are. The similarities, I mean. It's pretty interesting, huh? All right, so I have a few examples for us we can try. All right, let's see. Here's my first one. Find the area of the surface given parametrically by R of u and v, which is equal to v cosine u, v sine u, v, where u is between 0 and 2 pi, and v is between 0 and 1. From our earlier experiences, again, our assumptions that we made at the beginning, we know that this is actually a cone. Whose height is 1. Okay, we want to find the surface area of this. All right, so we're going to need the differential element of surface area, which is equal to this. All right, well, let's go get our partial derivatives. Partial r with respect to u. Zero for the last one, huh? Because the derivative of v with respect to u is going to equal 0. Then partial r with respect to v. All right. Then we take the cross product of these. Okay. Take the cross product of this and we'll get the following. Then the magnitude of that. Okay, so we want to square all three components, add them together, take the principal square root. Verify that we'll get this. So then our surface area okay. All right, now region R is in the UV plane. Quick little sketch of that. And we said that above, right? We said U was going to range from 0 to 2 pi, V from 0 to 1. So my figure would look like this. Okay, nice little rectangle. And I'll set up my iterated integral. Okay. And that, again, kids, after that, that's just straightforward integration. Okay. I'll leave you to fill in the details. Your final result should be pi root 2. Okay. Here's another example for us. Okay. Find the area of the surface given by the following vector value function, where u ranges from 0 to pi over 2 and v ranges from 0 to 2 pi. You recognize what that surface is? Yeah, good, good. From your experiences, you know this is a sphere. Good, this is a sphere, right? And actually, and based on these, again, u ranges from 0 to pi over 2, v from 0 to 2 pi. Remember from your experiences, we think of spherical coordinates, right? These look like spherical coordinates, or the spherical, or the equations, the components in spherical coordinates form, if you will, where u would take the place of phi, and v would take the place of theta. Okay, good, good. All right, so here's a quick sketch of our hemisphere. Oh, that's terrible. Oh my goodness. I am not going to be artist of the year. Oh, my camera's a little blurry. It'll come back. Let's see if I can put this under there and make it come back. There it goes. Sorry about that, everybody. That's my cheesy camera. All right. We need the partial of r with respect to u. Okay, so I take the derivative component by component with respect to u. My partial derivative of r with respect to v. Take the cross product of these two vectors. Ran out of room here. I'll go over here. Okay. Then I need the magnitude of this. Okay. So I want to square all three components, add them together, and take the principal square root. And when I do, when all the dust settles, I'll wind up with this quantity, which you can verify. Okay. So this, then, my differential element of surface area, becomes this. All right. Now my integral for the surface area like that. And of course, when we set up the iterated integral, okay, maybe this one will work out a little bit more. So our antiderivative of 100 sine u is negative 100 cosine u from 0 to pi over 2. Okay, apply our fundamental theorem. Going to wind up with a 100, and I'll just bring that through the integral symbol. Okay? And of course, the value of our integral is 2 pi. Okay. All right, now my next example, everybody, this is going to be an example of a general surface integral. Okay. So evaluate the surface integral x squared plus y squared plus z squared, where S is the sphere, x squared plus is the unit sphere, right? Because the radius is equal to 1. Okay. So for this one, the parametric equations of our surface are going to be these. Mind you, now radius is 1. Okay, so that's the whole sphere. Okay. And I'm going to steal a little bit of the solution from the previous problem, and I'm going to say that the differential element of surface area is equal to this. Okay, now don't you take my word for it. You verify that. Okay. You verify my work. Okay. Really, what I was doing though, everybody, I was just remember this is similar to the previous problem that we just did. So I just borrowed a little bit of the work. Okay. All right. So my surface integral then is going to look like this. Okay. Now, first of all, x squared plus y squared plus z squared, well, that can be replaced with 1 based on this equation right here. ds, well, I've got that right here. Okay. And I'll leave the details to you. Should get 4 pi. Okay. Now, my next problem, finding the surface area of that part of the plane in the first octant. Now, again, before I do this, I'm going to make a remark here. You've seen that a surface can be given parametrically. Remember, that was one of the assumptions we made at the beginning of the video. Yeah. But suppose the surface S is given by the equation Z equals G of X and Y. Then maybe we write like this. Yeah, what do you think about that? And then this expression, right? This expression becomes this expression. All right, so what does that look like? Well, first, find the cross product of these two vectors. And let's see. Partial r with respect to x is 1, 0, and the partial of g with respect to x. And the partial of r with respect to y, well, that's going to be 0, 1, g sub y. So when I take the cross product of these two things, I should get this. And that gives me this, right? You have to square all three components, add them together, and take the principal square root. So I think I'm going to use this for this particular example. In other words, I'm not going to use a parametric version for this one. Okay. All right, let's see what we're dealing with here. Okay, this is a plane in the first octant, and I'll use its intercepts to graph it. Let's see. Looks like we're going to get 6, 4, and 3. Okay, so there's our plane right there. Okay, move that up a little bit. And my z equals g of x and y. If I take the equation of my plane right here and I solve it for z, I'm going to get the following. Okay, that look okay? All right, then my differential element of surface area in this case, which is right here, times dA is going to be the following. Let's see. Partial with respect to x is negative 1/2. Square that. With respect to y, negative 3/4. Square that. Plus 1. Which simplifies to the square root of 29 over 4 dA. So my surface area integral, capital S, becomes the following. Okay, how's that look? Now notice that the integrand simplifies down to just a constant, everybody. So I can set that constant aside. like this. And remember, what does that integral represent? Good. It's the area of the region R. Now, where is the region R? Good. It's in the XY plane this time. It's in the XY plane. And let's see, based on our figure right here, our region R is going to be this triangle. So 1/2, the base is 6, and the height is 4. Whole thing simplifies down to the 3 times the square root of 29. Didn't actually have to integrate at all. I love those problems. Remember, gang, remember, the best integral is the one you don't have to integrate. All right, very good. And since we're talking about surface integrals in rectangular form, not parametric form, I've got one more. Okay, we want to evaluate a general surface area, surface integral rather. Okay, and I'm not gonna use the parametric form this time. Okay, I'm gonna do just like I did in the last example. Okay, so this is my surface S. Okay, and notice I can rewrite that like that. Okay, S is the sphere. You know what, gang? I copied this out of a book, and the rest of the directions were the upper half of that surface. Okay. All right, let's see. So our integral, we're going to have to rewrite it like this, where ds is equal to this quantity from our previous example. Okay, so what I'm going to do is what is my function little g? Well, that's right here, gang. That's my little g right here. Okay. All right, so let me go over here because I think this is going to take up a little bit of space. Okay. I am going to switch out the letter z for what it represents here. So square root of 36 minus x squared minus y squared. Okay. And then this quantity right here, I've got to find the partial derivatives of this expression and square them. Okay. Oh, that's a mess, isn't it? Don't lose faith. Don't lose faith. The problems are always contrived, aren't they? Don't lose faith. Okay. All of this, gang, I'll leave the algebra to you. I'll leave the algebra steps to you. But all of this under the square root symbol simplifies down to just this. Okay. Algebraically, we're going to be able to cancel these. Okay. The square root of 36, I'll just move that through the integral symbol like this. Like that. All right, not too bad. Now, what I would do now is remember, again, where's dA? It's in the region R. Where's the region R? Is in the XY plane. So that means we're going to need the shadow of the surface on the XY plane. Well, as we said at the beginning of the problem, our surface is the upper hemisphere, sitting at the origin whose radius is 6. Okay, so that means our shaded region is right here, okay, in the XY plane. Okay, I would definitely use polar coordinates on this. Okay, take a look at that. How's that look? Right, the region, we've got the quantity x squared plus y squared. That's reminiscent of polar coordinates, right? X squared plus y squared is r squared. Plus, we've got that nice circular region, which is a nice polar region, right? And so its limits, theta is going to range from 0 to 2 pi, of course, and r is going to range from 0 to 6. This result here is perfect for polar coordinates. After this, it's just straightforward calculation. Going to integrate with respect to r first. Mind you now, r squared times r is r to the third. Notice r equals 0 is not going to make a contribution here. Just the 6 will. And that's a constant that I'll just set aside. Okay. Final answer. Okay. So just some nice examples of surface integrals where we either calculated surface area or general surface integrals. And whether we did those in parametric form or rectangular form, I will say this, they're a little on the tedious side. All right, but hopefully got a nice little a nice understanding of how to use surface integrals. We have a really nice application of those. They're called flux integrals, and maybe we'll do that in another video.